Okay, so let's take a look at um, the data sheets for these transistors that we've been looking at. Let's see which one we have here. Okay, so this is the 3904 transistor. If you look at your look in your notes, we use the 3904, or the book like to use the 2N22 or 2222 NPN transistors are very popular. Um, I know this one almost by heart because I've used it for so many years when I was, especially on my first job designing stuff. I know that the maximum continuous collector current for this transistor is 200 milliamp. So if you don't know anything, grab a couple of, if you did what I did, and that was to basically build little circuits. And so I got to have an idea of what a particular transistor would do. So this is the 2N3904 NPN transistor, collector base emitter. If you look at the case here, and this is a what's called a TO92 package, so epoxy package with 3 legs on it. So this is intended for through hole, go into the board, as opposed to surface mount, which would sit on top of the board, and you solder to some little packet, just to some pads. So here you look at the schematic, excuse me, the package. We have pin 1, pin 2, pin 3. Pin 1 is your emitter, pin 2 is your base, and pin 3 is your collector. Now, if you don't remember which one is your collector, which one is your emitter, if you know which one is your base, which is the center, you can actually, with an ohm meter, figure out whether this is a PN or NP junction here. So, for example, if I look here, I have an ohm meter and I put positive terminal here and then negative terminal here. I'll actually get current flowing in this direction, which means I know this is P and this is N because this is a diode junction. So this would be P and this would be N. So now the question is, yeah, but if I put positive here and negative here, this is also a PN junction. There's a diode junction here also. So how do you know which one is which? But if we ever get to the lab, we can actually play with this and you can figure out whether it's a PNP or NPN transistor just by knowing one of the terminals, or actually through elimination. If I didn't know that this was the base, I could still figure out whether or not this was an NPN or a PNP transistor, and eventually figure out whether where the collector was, the emitter, and the base. Okay, so what I want to look at though is some of the parameters for your transistor. So here you have, go here. So here's your collector and here's your emitter. So here's your collector emitter voltage. This parameter here tells you the largest voltage you could put across your collector emitter before you do any damage to it. So in this case, it can actually withstand up to 40 volts, which is pretty good. Then we have the collector to the base, which is between here and here. And that can withstand up to 60 volts before it breaks down. But there's a diode junction here. So you're actually looking at the reverse breakdown voltage of a diode. And then your emitter base voltage, your emitter to base reverse bias diode here, it can withstand up to 6 volts with this being positive and this being negative before it breaks down. Okay. And then you have your collector current, your maximum collector current, the current that can flow through here, is 200 milliamps, which is actually a pretty decent amount of current for such a small device. Power dissipation, this transistor can actually dissipate up to 625 milliwatts, so more than a half of a watt through this little ceramic package before there's any type of damage done to it. And that's when the ambient temperature is 25 degrees C. Let's see what else we have. So when you're storing or operating this device, it'll actually operate up to 150 degrees C internal junction temperature and down to a minus 55 degrees C internal junction temperature. So yeah, you could use this in some type of, say, automotive application where it gets really hot under the hood, or some environment where it actually gets really cold. So those are your electrical, what's called your maximum ratings for your electrical, some of your electrical and thermal parameters. Here you have more thermal characteristics. This is basically the thermal resistance between your junction and your ambient. We won't talk too much about power dissipation right now. And then here, when the transistor is actually off, what the breakdown voltages are. So the base emitter junction is off, and you can put 40 volts on it and it still won't conduct. What we want to look at is, we come down here to our on characteristics. Tell you what, excuse me 1 second. Yeah, excuse me 1 second. Okay, thank you for waiting for me. So the 2N3903 is another transistor that's similar to 2N3904. Slightly less performance, but 3904 is actually more common. So here we have things like this symbol here, HFE. That is what we refer to as beta, or your current gain. You see it here, DC current gain. So for a collector current of about 10 milliamp and VCE, a collector millivolts of 1 volt, for the 3904, we have a minimum beta of 100 and can be up to 300 for your beta. So we've used 100, 180, 200 for beta. It can actually be as high as 300. But beta is also a function of current. So as we change our current, our beta value will actually drop off if the collector current is too low, and it'll actually increase and drop off. Oh, actually, you can see it here. So when the collector current is 100 milliamp, you'll see that for the 3904, the minimum beta is like 30. And when we're 50, is at 60. So the sweet spot seems to be right around 10 milliamp for your collector current, where you get your maximum beta. If the current gets even lower, like 1 milliamp, the beta starts to drop, and at 0.1 milliamp, it drops down to like 40 for your 2N3904. So you'll see that there's actually a curve for your beta as a function of current. That goes up and then it drops down on the high and the low end. So you want to bias it ideally somewhere around 10 milliamp for your maximum beta. Small signal characteristics. Here's your current gain as a function of frequency. And we were doing the high frequency pole location. There was one called F sub T. This is where your beta actually drops off. And if you go back and look at the notes, it's actually, this one is usually associated with your second highest frequency on your high end. It's not your dominant pole. There's actually another device or parameter that sets your dominant pole. So here's our output capacitance. In the textbook, we call it C out between the base, C out, excuse me, at the base with, and it's like 4 picofarads. Then you have CNBO, which is about 8 picofarads. So again, if you look back at some of the problems we worked for looking at your high frequency poles, you'll find that we were given these parameters. Let's see, and you have input impedance, voltage feedback ratio. Some of these what's called H parameters we won't get into. The one that's most important that we usually talk about is this guy right here, HFE, which is the same as beta, your small signal current gain. Let's see, and then you have switching parameters when you're using your transistor as a switch as opposed to an amplifier. Okay, let's see if there's something here quickly I want to see. This capacitance. Looking for your beta or your HFE as a function of current. And yeah, here we go. HFE or your DC current gain as a function of current. And you'll see here at about 10 milliamp for your collector current. At high temperature, your current gain actually is a function of current, is also a function of temperature. So here's room temperature at 10 milliamp. If we increase the temperature, the junction temperature to 25 degrees C, our gain actually goes up. And if we decrease the temperature, our gain actually goes down. But we'll see here, this is what our beta or HFE looks like as a function of current. So too high a current and we start to lose gain, too low a current and we start to lose gain. So there's a sweet spot right here in the middle where you usually find these transistors biased. See, there are other parameters that we're not going to talk about now. Okay, so that's your NPN bipolar transistor. There's also, and maybe we'll look at this tonight, if not next time, when we're looking at your common source amplifier that uses an N-channel MOSFET transistor. And so we look at the IRF 610. The symbol looks like this. This is N-channel transistor. And this is what the package looks like. This is a 220, it's called a TO220. It's a larger package than the NPN because it's going to handle a lot more current. So usually the larger the package, the higher the current rating. And absolute maximum ratings for the transistor. The drain to source voltage, this can handle up to 200 volts before it breaks down. So it's usually a higher power application and a higher voltage application than your NPN transistor. Your gate to source voltage here is plus or minus 20 volts before you get a breakdown. Remember, your MOSFET actually, between your gate and your source is actually a capacitance. So you typically don't have current flowing between your gate and your source. But this can withstand up to plus or minus 20 volts before you do any type of damage to the oxide in that capacitance, and you actually get current flow. And look here, the maximum power dissipation here is 43 watts, as opposed to, what was it for the NPN? The 3904, I think, was like 625 milliwatts, or less than, basically a little more than a half of a watt. This can handle about 80 times that as far as power dissipation. Okay, so we'll come down here to some of your more electrical parameters. See, drain to source breakdown voltage. So this can withstand up to 200 volts between your drain here, if you can see my cursor, and your source. So we can use this in higher voltage applications. The gate threshold voltage. So it'll turn on with a minimum of 2 volts between the gates and source, but maybe as high as 4 volts between here and here before you actually get enough what you call inversion in your channel to get significant current flow. And see, is anything else we want to cover here? Yes. I really want to try to get to, since we're talking about frequency response, is capacitances, device capacitances. So here, your input capacitance denoted by C sub ISS for this transistor is like 135 picofarads. Your output capacitance, COSS, 60 picofarads. And we call your reverse transfer capacitance, CRSS. That's the capacitance between your drain and your gate, will be 16 picofarads. So, okay, so what does this have to do with our frequency response stuff? If you recall, and if you don't, I will remind you. So we're looking at we're interested in our gate to source capacitance, our drain to gate capacitance, and our drain to source capacitance. That's actually included in these parameters here. So let me see if I can find, I had it a second ago. One moment. Yeah, here we go. Let's see if we can switch over to my other camera. Here we go. Let's see. We share. Oh, I'm sorry. I need to turn it on. Turn this on. One second. Let's get this straight. Okay, stop sharing for a second. And share screen again. Okay, there we go. So let's see if I can zoom in here. Okay. So let's start on this side. So for our common source amplifier here, this is our IRF 610 transistor that we're looking at. So all the other stuff we can get from the schematic, but for the high frequency pole, we'll need to know the or access the data sheet for the transistor. Then here, this way. Excuse me a second. I'll block you here. There we go. So here's our, let's zoom out one. Okay. So here we're trying to calculate our, this is low pole frequency response because it's C sub C and C sub D, C sub S. These are these capacitors here, and the other one on the other side over here, which you can't see. Then we're doing our high frequency analysis. We'll need to access the data sheet. I'll see if I can zoom in a little bit here. There we go. And you'll see we'll need to know our gate to source capacitance. We'll need to know our drain to source capacitance, and we'll need to know our drain to gate capacitance here. So our gate to source capacitance is our C sub ISS minus CRSS, which was given in the data sheet. Although the book here says 135, the data sheet I was looking at, this is 130. So it'll be about 125 to 130 picofarads for a gate to source, this capacitance here. For gate to drain, the capacitance across here is what they call CRSS, and it's just 15 picofarads. And then for our drain to source, from this node to the source here, it's COSS minus CRSS, Wherever my CRSS is here. And so that ends up being about 38 picopairs from here to here, from here to here, and from here to here. So from using our data sheet, we can get our device capacitances. And then from there, we can use Miller's theorem. Yep, there we go. To calculate, scroll down some. Miller's theorem and our gate to source capacitance, which we just calculated, and a gain, which we had calculated earlier to give us our C Miller in, our C Miller out is gate to source capacitance times our gain factor. And then our C in, input capacitance, is going to be the C Miller in plus the gate to source. And the C output capacitance is going to be C Miller out plus C drain to source. So with all that, we can calculate what our high frequency poles are. So we have one here due to the input capacitance, which is this. Another one here due to the output capacitance, which is this. So 12.5 kilohertz and 1.365 megahertz. Just to point this out, so this is a MOSFET. It handles a lot more current, but it also has a lot lower bandwidth because of these device capacitances. So we'll get more power. And remember, I mentioned the gain bandwidth product, so we can get more gain, but we'll have to sacrifice bandwidth to get it, or we can get more bandwidth, but we'll have to we're willing to accept a lower gain in order to realize that. And so here, for your MOSFET device, or your your common source amplifier, all the equations you need to calculate your low frequency pole response and your high frequency pole response. And for the high frequency analysis, you're going to need to have access to these device parameters or the data sheet. I miss it. 702. Okay. That's all I wanted to mention about that, to show you how to look at the data sheet and where to find some of this information that you may need in order to do, if you're trying to do some type of design, or if you're trying to verify some design to make sure this person actually designed it right. Being able to go to the data sheet and get the device parameters that you need and basically plug them into these equations to see whether or not you get a ballpark figure that's correct. And that's really all design really is. It's either knowing the information or knowing where to get the information. And after that, knowing what to do with the information. Okay. Okay, so let's stop sharing. Here. Okay, any questions about any of that so far? And I'll make a copy of these data sheets and I'll send them to you. So familiarize yourself with some of the parameters that you'll need in this class, specifically your HFE for your bipolar transistor, and your CISS, COSS, CRSS for your MOSFETs, and your, was there something else? Oh, your beta, your HFE, I mentioned that, for your bipolar transistor. So if nothing else, when you got this class, you should at least be able to look at a data sheet and says, oh, the beta of this the current gain of this transistor, or the beta is so and so for this value of current, because I can at least look at the data sheet and understand where some of this stuff is, even if you don't understand all of it. To understand all of it, we would actually spend more time. Actually, I would find it fun doing, but we only have so much time. We could take a transistor, go in the lab, and measure all these parameters ourselves, set up the little circuit, and the test circuitry is not very hard, but you'll learn a lot more about the device and how it works if we had time to do something like that. But unfortunately, we do not. Okay. So we looked at frequency response for an RC, and frequency response for a C and an R. We looked at the frequency response for a bipolar transistor and saw that the capacitances that we add to the circuit, either the coupling capacitors to block out the DC, or the bypass capacitor in the case of a common source or a common emitter amplifier to bypass the resistor to actually increase the gain of it, all set pole locations. That is actually what gives us our low frequency pole response. And then our high frequency pole response are usually always dominated by our internal junction capacitances, which you don't get to change. You can choose a different device, but once you get a device, what you get is what you get as far as your high frequency pole goes. Okay. So that's all I want to cover for tonight. I will send you the data sheet so you will have them. Because when I give you the assignment, you will need to be able to look up some of this stuff. Okay, 1, 2, 3, 4, 8, 9, 10. Questions or comments?
No questions right now.
Okay, Ms. Robinson, thank you. Thank you very much. Okay, that's all I was planning on covering for this session. We will meet tomorrow evening, and I will. And if we do not, I will send out an email. But plan on meeting tomorrow evening, and I will send this stuff out to you this evening. And I want to